Hello, and thank you for joining us for today's webinar on school assignment algorithms and market design with Professor Parag Pathak. My name is Greg Bybee, and I'm one of the co-founders of Avella, and I'll kick us off. So what we're going to cover today is I'll start with some quick introductions, both of ourselves as well as Avella, and then I'll turn it over to Parag, who will go into a deep dive on matching markets, algorithm design, great properties, and then we'll have a lively discussion. Please feel free to jump in throughout the webinar with Q&A in the chat, and we'll try to answer them as we go. So our society is finally confronting the hard truths of systemic inequality and implicit bias. Governments, schools, and organizations are reevaluating how they make decisions and allocate resources. And they're turning to Avella because our mission is to fight systemic inequality in education and increase access to educational opportunities. We believe it's very important for school districts to operate more efficiently, more equitably, and to empower their communities. And a lot of the way we do that is through the algorithms, which we'll discuss today. We've already had tremendous impact. At Teach for America, core member teacher satisfaction has been able to increase 33%. In New York, 30,000 more students were able to choose a preferred school. And in Denver, our research showed that this increases student achievement by 0.4 standard deviations. We do this by working across the spectrum, starting with family communication and information through the application process, the admissions lottery and assignment processes, through funding allocation. And our product suite aligns to this, from Avella Explore at the front end, through our application suite, to Avella Match. And let me talk about those two a little bit. Avella Explore is our school finder and enrollment guide. It's designed to be incredibly equitable and accessible. It's mobile optimized for easy use on mobile devices. It works in multiple languages. It's accessible, and it's very easy and user-friendly. There's no need for a login. There's no walls. There's no wizards. Come to the website and you get the information you need immediately. We also give recommendations. We encourage ranking. We encourage families to look at more schools, and we make it very easy to understand enrollment deadlines and processes. We also offer a matching platform called Avella Match, which is used for centralized school assignment and is capable of designing and running these enrollment lotteries. And this is really a lot of what Parag is going to talk about today, the secret sauce behind Avella Match, which are the algorithms. Now, Avella Match is designed to be easy to use, intuitive, user-friendly. You can drag and drop different fields and create these lotteries, run scenarios, do experiments, and kind of see what the results will be. And then when you actually want to run the final lottery, we'll log it and make sure it's auditable and transparent. Behind the scenes of this are Nobel Prize winning algorithms. In fact, Parag's advisor, Al Roth, won the Nobel Prize for his work applying some of these algorithms to school enrollment, as well as kidney exchange and the medical residency program. And our company was founded by Parag and Josh, who are two of the leaders in enrollment design and algorithms. And with that, actually, let me turn it over to Parag. So I'll introduce Parag. He's one of my co-founders of Avella, and he's our chief economist. He's also the class of 1922 professor of economics at MIT, where he studies market design, matching algorithms, and school enrollment. He founded MIT's SEII, the School Effectiveness and Inequality Initiative, recently renamed to Blueprint, which studies these issues. And he also co-founded NBER's working group on market design. Perhaps most impressively, he's the winner of the John Bates Clark Medal, which is the second highest award in all of economics, specifically for his work applying these algorithms to student enrollment within schools. I'm excited to introduce Parag.
Great. Thank you so much, Greg, for that introduction. And thanks to everyone for logging in today. I'm really excited to tell you a little bit about school assignment algorithms. That's something that I've spent my entire career on and something I think is incredibly important. Before we jump into my part of today's webinar, I'd like to kick things off by asking the participants today to tell me a little bit about yourself. So we're going to launch a poll and ask you to fill it out. What's your primary role? please take a look and please let us know who you are. Okay, I think we just need one or two more participants and we'll close the poll. Terrific. So welcome everyone. We have a large group of district administrators, CMO administrators, researcher and professors, advocates, consultants, and other. I'm very eager to hear feedback from all of your perspectives. Let me kick things off today by telling you a little bit about matching markets and what is a matching market and why it differs from usual markets that folks like me, economists, have studied over the years. So in many traditional types of markets, think about the stock market or commodity markets. When something is scarce, the individuals who are willing to pay the most get what they want. So if you've ever tried to buy a house, you know, the way that works is whoever pays the most for a house will outbid everyone else and be able to get the house. And that's a good a framework for thinking about many of important transactions. But for many other important life transactions, money isn't everything. So not only do you choose something, but you also have to be chosen. So I'm a professor at MIT, and one of the most consequential decisions involves getting into college. And for MIT, I can't simply choose to go to MIT. I can't simply pay more than someone else to get access to MIT. I also have to have MIT pick me. Okay, so that's two sides, what I want and what the university wants. Another example is choosing a spouse. Okay, so I can't simply choose someone to partner with, but my partner also has to choose me. And a third example involves getting a kidney donation. So if I need a kidney, maybe I have end-stage renal failure, I can't simply buy a kidney in the United States. In most countries in the world, that's illegal. I need to have someone donate their kidney to me. So these are all situations which economists call matching markets, because we don't have the usual price instruments, and we have two sides. So in contrast, in usual economic markets, the price is a very important way for the market to equilibrate. So prices are determined by the point at which the demand in this situation in the market equals the total supply in the market. So if the demand is greater than the supply, we usually expect the price of something to increase. And on the other hand, if the demand is less than supply, we expect the price to decrease. So that's what I mean by equilibration. Price is going to be the point at which demand is exactly equal to supply. And in a matching market, when we don't have access to a price, we have to think much more carefully about how the market is going to equilibrate. So what is the supply? What is the demand? And how would we match those things up? How would we clear the market? And that takes us to the topic of today's webinar, which is an algorithm. So an algorithm is the mechanism by which we will match together demand and supply. And in the context of K through 12 education, the supply here are simply the seats at schools. The demand is what families want. And in a choice system, an algorithm is what's going to equilibrate demand and supply. Now you might be thinking, well, how do we actually equilibrate demand and supply in the big parts of the United States where there is no choice system? What does the equilibration? And here what typically economists say is, well, there's no algorithm. The equilibration, who gets to go to what school, is determined by the housing market. So in the suburbs of Boston, there's differences across neighborhoods, and if you want to get access to a school, you have to get access to the housing market in the surrounding neighborhood. Okay, but in big urban cities, including cities that many of you guys are from, we have choice systems where we have to think about rationing or clearing the market in a different way. Okay, so let's turn now to algorithms. And algorithms are sometimes seen as a scary word, but In a nutshell, an algorithm is simply a way to go from a set of inputs into a set of outputs. Okay, so more precisely, it's a set of ordered steps for solving a problem, such as a mathematical formula or the instructions in a program. Okay, the algorithms are all over the place, and when we think about school assignment, the ingredients here, what are the inputs? The inputs are the students' preferences, where they want to go, the school's capacities and their priorities, that's the supply side. By priority, I mean, do we allow sibling applicants to get in ahead of children who don't have siblings at the school? Or is there some consideration for neighborhood preference? The output all the way here on the right is an offer of assignment for each student. And that could also include students not getting an offer. Okay, and so what the algorithm is doing is taking the inputs and constructing the outputs. Okay, so the algorithm is the assignment process. It's the step where demand is matched to supply. Okay, now you might be wondering, why do we need an algorithm? Well, you need an algorithm when you cannot give everyone what they want. The key problem that necessitates having an algorithm is that there's not enough resources to make everyone happy. There's no way to give everyone their first choice. So we need to have a process to determine who gets one of their choices. And that's really important. You know, ideally, and something that we all hope for is we'll be at a position where we can give everyone their first choice. But until we get to that point, we have to solve today's problem, which is to come up with a fair and efficient way to give people choices that they want, subject to the constraints that we have in the system. Okay. Now, based on the previous diagram, I hope you see that the algorithm is just one part of a much larger school choice ecosystem. And if you want to have a good algorithm, one of the most important things are actually the inputs to the algorithm. Okay, so how do we have families make effective choices? How do they learn about schools? What kinds of decision aids are out there? How do we give information in open houses? Do we have nice school finders like the Avella Explore product that Greg just mentioned? Another key input is how should we decide on school priorities? Should we have a neighborhood priority? Should we have some consideration for diversity? And what would the effects of those kinds of policies be? And even more general than that are thinking about when you run a district or you run a set of schools, what should be our portfolio of schools? What type of programming should we offer? What type of curricula should be made available? Should we give busing to everyone? Should we restrict busing only to particular zones in the city? These issues are incredibly important, but for today's purposes, I want to separate these issues out from the algorithm, okay? And stay tuned. We will have future webinars where we touch upon some of these issues as well and understand how they might interact with the algorithm. Okay, so now let's turn to some properties of an algorithm. And by that, I mean, what makes an algorithm good? What's going to make an algorithm be effective or have desirable properties? And so there's many dimensions here. Some of the dimensions are algorithmic. So let me start with those. The very first thing that is important for a good algorithm is it makes it easy for families to rank schools, okay? And so we want to allow people to exercise choice in a fair and easy way. So an algorithm should try to make that as easy as possible. The second thing I have listed under algorithmic dimensions is an algorithm should give as many families as possible one of their top choices, okay? And lastly, can you make sure that no families can complain about their assignment and be justified in their complaints, okay? And so that last property is a property that's related to equity. If we have situations where someone can complain about what they got, I'd rather go to another school and I have a higher claim to that other school because it's a testing school and my score is higher than someone who got the school, then that's going to be undesirable. And what I want to illustrate is, unfortunately, all three of these properties, making it easy for families to rank schools honestly, giving as many families as possible their top choice, and avoiding situations where families have justified complaints is mathematically impossible, okay? So that raises the question, how should we trade off different attributes of an algorithm when you can have it all, okay? So that's what I'm going to turn to next. But before I turn to that next, I want to actually emphasize one other key part of an algorithm, which is the fact that you have a process that's automated raises questions about whether you can explain your process to participants, okay? Can you actually give them advice? How should I rank schools? How should I participate? After you run your algorithm, can you actually audit it? Have you kept good records on who got to go where and why they got to go where? And finally, can you use your process to drive continuous improvement? And that's a longer term goal that we hope to enable with systems like this. Okay, so let's now start with the first three questions. Can you make it easy for families to rank schools? Okay, so this is the very first property, and I'm calling it honesty is the best policy. Okay, so you know, if you go through a system of choice, it's very complicated. It's also very stressful. Families spend a lot of time worrying, fretting about what's a good choice, whether one school is a better fit for their child than another school. And once you've done that, there's another step, which is, should I tell the assignment system what I want honestly? Okay. And often, especially in single best offer assignment systems where children get at most one choice, a family submits a ranking of schools. And we often hear, and we've seen this across the United States, questions about whether a family should actually avoid ranking a school that's really popular. Maybe I'll have a better shot of getting one of my choices if I stay away from the most sought after schools in the district. Or families often wonder, should I rank schools where I get a very high priority, maybe where my older brother is attending? And an assignment system where parents are not rewarded for reporting their choices dishonestly is what we call a strategy proof system. It's immune, it's proof from strategic behavior. And by strategic behavior, I'm simply referring to, once I know what I want, should I actually honestly report that to the system in my application form? Now, why is this an important property? Is this kind of something that economists only talk about? And I want to say no. And I think the best way for me to make that clear is to go through a couple of examples of systems that we've seen in the field that do not have this property. Okay, and the starting point for this is actually Boston, Massachusetts. So several years ago, economists who study these kinds of processes brought some attention to the system that Boston was using at the time to place children into schools. And they pointed out here, this article says that students and families may have a reason to lie about what schools they want. Okay, so let me explain what this article is about. This article went on to precipitate a change in the assignment system in 2005. Boston's system at the time is an example of what we call an immediate acceptance system, okay? And in an immediate acceptance system, as you're processed, as your choices are processed, you are immediately assigned. So no assignment is ever undone. How it works more specifically is in the very first round, we have a set of student preferences and we have a set of school priorities. Those are orderings of students. We only consider students' first choices. And for every school, we look at who has listed that school first, and we assign students one at a time in order of the school's priority until either there's no seats left at the school, so we filled up the school, or there's no student left who's listed as their first choice. If I am lucky enough to be accepted at that point, I'm immediately accepted. My assignment is finalized, and I'm done. Okay. Any student who did not get their first choice goes on to the subsequent round. And in the generic round, round K, we'll call it, we only consider the kth choices of students. So if this is the second round, we'd only consider the second choices of students. We look at any school that still has seats left over and consider every student who's listed as their second choice who hasn't yet been assigned. And we'll assign seats at those schools to the students in order of priority, one at a time, until either there's no seats left or there's no student who's listed it as their Kth choice, okay? So the key thing here is that you are immediately accepted if you're good enough to qualify in terms of priority at your first choice. So this sounds like a very intuitive idea because we're trying to give everyone their first choice. And it has one very important flaw, and that flaw is it's challenging to figure out whether I should list my first choice honestly or not. Should I go for the first choice that I really want, or should I be a little bit more careful and choose a first choice that's realistic? Okay, and let me illustrate that problem when we think about a hypothetical student, Estella, choosing school. So in Estella's case, imagine she has 3 different schools she's considering: the Murphy School, the Channing School, and the Perkins School. Now, these are actually schools in Boston, and Estella likes the Murphy first, the Channing second, and Perkins third. The table here is showing what her priority is at each of the schools. In Boston, the priorities are a priority for sibling status and a priority for walk zone status. And here at the Murphy School, Estella has neither sibling priority nor walk zone priority. At the Channing School, she has sibling priority, and because sibling priority comes ahead of walk zone priority, she stands a pretty good chance of getting the school. And then finally, at the Perkins School, she has no sibling priority, but she lives in the walk zone, the geographic catchment area around the school. So here's the question that we face. Should Estella list the Murphy School first? Now remember, at the Murphy School, applicants who have a sibling and live in the walk zone come first, then applicants who have a sibling, and then finally applicants from the walk zone. And then lastly, none of the above. So in this case, at the Murphy School, there are 3 categories that come before Estella's group because she has neither sibling nor walk zone priority. At the Channing Schools, Estella has sibling priority, so she's likely to get an offer there. So let me pause for a second and ask you, what school do you think Estella should rank first? Should she be honest and list the Murphy as her first choice? Or should she instead list the Channing as her first choice where she has sibling priority? So there is a poll that's hopefully on your screen. Please take a moment to fill out what you would do if you're Estella. Just a couple more folks need to answer. Terrific. Okay, thanks everyone for filling this out. And the summary of the poll is about half of participants said list the Channing first, okay? The other half say list the Murphy first. So half of the participants here are saying you shouldn't be honest, you should lie, you should be strategic and actually rank a school that's not your first choice as your first choice, okay? And that indeed is something that many family members think about in situations like this. Now, it's of course very challenging to know the right answer here. I haven't told you enough about the scenario. I haven't told you enough about how competitive the Murphy is, how many other kids want the Murphy. I haven't told you whether Estella has a good random number or a bad random number. I haven't told you about the same kinds of considerations at the other schools. And so in some senses, this is a little bit unfair of a question because we don't know the right answer, but I don't think it's an unfair question if you put yourself in the seats of a parent going through a system like this, because they're unlikely to know what the competition is at the Murphy versus the Channing. In some cities, you don't know what your random number is, and you face this high stakes gamble. Should I rank something that I really want, the Murphy, or should I rank something that's a safe choice, the Channing? It's a safe choice because I get sibling priority there. And this is something that several families in Boston figured out in the early 2000s. Parent groups formed to talk about heuristics, how to navigate what are the demand patterns at schools like the Murphy and Channing. And eventually Boston moved away from a system like this, okay? Now, in terms of how to participate in other places across the country where we see systems that reward dishonest behavior, we see a lot of discussion about how do we play in one of these systems. So here's a quote from the St. Petersburg Times in Florida. It says, "Make a realistic, informed selection on the school you list as your first choice. It's the cleanest shot you'll get out of school. It's the cleanest shot you'll get out of school, but if you aim too high, you might miss." Okay, so this is very similar to our example. They go on to explain, here is why: if the random computer selection rejects your first choice, your chances of getting your second choice schools are greatly diminished. That's because you then fall in line behind everyone who wanted your second choice school as their first choice. You can fall even further back in line as you get bumped down to your third, fourth, and fifth choices. Okay, so do I go for the safe choice or do I go for the school that I really want? Here's another example of a system like this used in the field. And I'll let you look at this article in detail. I won't read it, but what it essentially says is in the city of Chicago, for their elite exam schools, there's 8 of them at this time, Chicago actually used the immediate acceptance algorithm, got rankings from over 15,000 participants, and then they said, this is unfair, okay? They say high-scoring kids were being rejected simply because of the order in which they listed their college prep preferences. If you look further in the article, it says previously some 8th graders were listing the most competitive college preps as their first choice, foregoing their chances of getting into other schools that would have accepted them if they had ranked those schools higher. Okay, so if I rank a school that's really competitive as my first choice, I may miss out at my second choice because my second choice fills up with students who listed it first. So the city did a do-over. Okay, so this was very public facing. 15,000 parents were a bit surprised to get letters saying, you can re-rank your preferences. We've made a great mistake here, okay? Now, another issue with a system like this is interpreting information about what families want as true measures of demand. Okay, so when Boston had a system like this, several commentators made the mistake of taking preferences at face value. So Charles Glenn wrote, in Boston, analysis of the first place preferences for 6th grade enrollments in 1989 and 1990 shows that the number of relatively popular schools doubled in only the second year of controlled choice. His interpretation is that the strong lead of few schools was reduced as others tried harder. And of course, we don't know if that's the case. Schools actually tried harder to get more students to list them first, or whether word got out that you shouldn't list the popular schools as your first choice because you're going to fall through the cracks and lose out at your second choice, and so on. And that's a bit the conundrum that's created by systems like this. Let me tell you one other thing, and I think this is quite stunning, actually. So in the United States, the immediate acceptance system is still quite prevalent, but in England, actually in 2007, section 2.13 of the School Admissions Code actually outlawed the immediate acceptance algorithm, okay? And in fact, what they call it in England is first preferences first, FPF. That's a very descriptive name for this system because we put a lot of emphasis on what schools are ranked first. Your first preference dominates the priority. If someone has higher priority at that school but has listed it second, and you have the lowest priority and you've listed it first, you will win. First preference is first. And in England, the rationale that they gave is a first preference first system is unnecessarily complex. And in fact, a few years before this nationwide ban, the Pan-London Admissions Authority actually adopted an alternative equal preference system to make the system fairer and simpler for parents. So at the time of this ban, about 1 out of 3 local education authorities throughout the United Kingdom stopped using the immediate acceptance algorithm, okay? So to summarize, why is property number one important? Honesty should be the best policy. You have to remember admissions always feels like a high stakes gamble. It's very stressful. And when the algorithm rewards dishonest ranking, it's even more true that families have a lot of anxiety with the system. Now, strategizing is imperfect. In fact, as we saw with our poll, we couldn't agree, should we list the Channing or the Murphy? And the reason it's quite imperfect is we don't know what schools other families are choosing. We also don't know how much better, say, the Channing is than the Murphy. Should I take a shot at the popular school or not? And one big problem with this is that some families may be in the know and some families may not be aware of these rules. The families that are not aware of these rules may rank very popular schools and then end up in the administrative assignment bin because they're unassigned. The families who did figure out these rules may feel like the system is not trustworthy because they know that they shouldn't behave honestly. So rewarding dishonesty can undermine trust for both of these groups. And then finally, the choice data that comes out of these kinds of systems is not a reliable guide for scenario planning or understanding what families actually may want. Okay, so that's our first property, trying to make honesty the best policy. Let me turn to two other properties. I think the best way to describe these two other properties is in the context of an example. Okay, so how do we read this example here? So I have a situation where we have three students, okay, I1, I2, and I3, okay? And there's three schools, okay? So the schools are denoted by S's, S1, S2, and S3. And if you look at the preferences of the students, the rankings, what they want, in this example, student one likes school 2 first, and then school 1, and then school 3 is her last choice. Students 2 and 3 have the same exact preferences. Okay, so they both like 1 ahead of school 2 and school 2 ahead of school 3. Okay. At the bottom here, I have the priorities of the schools. Okay, so priorities here are in blue here, and the way to read this is at school 1, student 1 has the highest priority, followed by student 3, and then student 2. Okay. And at the other two schools, the priority places student 2 first, and then student 1 and student 3. So where do these priorities come from? In the background, this really is one of the key issues. It could be a sibling criteria, it could be a walk zone criteria, it could be some diversity criteria. For today, again, I want to abstract away from that and just say we have an ordering. Okay, there's an ordering who gets to go ahead of whom. Okay. Where do the student preferences come from? This is maybe because of geography or because of what families know, but let's assume these are the actual true underlying preferences, okay? So with that out of the way, let's turn to our next question, which is, can we improve the assignment of a student without harming the outcome for another student? Okay, so this is going to be our second property. If there's no way to make a student better off without harming another student, okay, we will say the outcome is efficient. Okay, so more concretely, let's say there's a student who got their second choice and there's still a seat left over at their first choice. Okay, we could have placed our student into their first choice and no one would have been displaced from the first choice. So that would be an example of a situation that's inefficient, okay, because there's a way to make someone better off without harming anyone else. Okay, so more technically, we would say an outcome is Pareto efficient if there's no way to make students better off without harming any other student, okay? So in our example here, what are the efficient outcomes? What are the situations where there's no way to make someone better off without hurting anyone, okay? And in this example, it turns out there's many outcomes that are efficient, okay? So let's just talk about a few. Let's go to our students here. Student 1, their first choice is school S2. So let's place them in their first choice. Let's now turn to student 2. Their first choice is school S1. So let's place them in S1, okay? Let's imagine, again, each school has 1 seat. And then finally, we get to student 3. Student 3, first choice is S1. That's already taken by student 2. School 2 is their second choice. That's also already taken by student 1. So poor student 3 is going to end up at their third choice. Okay, so the outcome where Student 1 gets their first choice, student 2 gets their first choice, and student 3 gets their last choice is an efficient outcome. Why is that? Well, who could be improved without hurting anyone else? Student 1 couldn't be improved because they're getting their first choice. Student 2 also couldn't be improved because they're also getting their first choice. So the only student who may want to get a higher ranked choice is student 3, okay? Now, student 3 is interested in school 1 and school 2, but unfortunately, all the seats are taken there. The only way for student 3 to improve is by making either student 1 or student 2 worse off, okay? So that's not a true improvement, because to make one student better off, you're making another student worse off. So the outcome where the first 2 students get their first choice and student 3 gets their last choice is an efficient outcome, okay? Let me just mention one other efficient outcome in this example, just to show you how things could differ and why we may need something more than efficiency to pick outcomes. What if we go to student 3 first and say, hey, you get your first choice. So 3 goes to school 1. Then we go to student 2 and say, you go next. Well, school 1's already taken, so we would place student 2 in school 2. And then finally, student 1 would be assigned their top choice among what remains. The only option there is school 3, okay? So that's an outcome where one student gets their first choice, one student gets their second choice, and one student gets their third choice, okay? So that's another example of an efficient outcome, because there's no way to make a student better off without hurting any other student, okay? Now, one thing I hope you've noticed as we've talked through this is that in all of my discussion, I'm only focused on the student preferences. I haven't said anything about the school priorities. And in fact, when we think about efficiency, the way we're defining it is we're saying, is there any way to make students better off without hurting other students? We've completely ignored the perspective of schools, okay? Now, we might be wondering about that, and that leads me to the last property I want to talk about today, which is a property that I call no justified complaints, okay? So the question we want to ask is, can a student complain about their assignment and be justified in their complaint? Okay, so what do I mean by having a justified complaint? Well, a justified complaint, okay, is one where a student wants another choice and a lower ranked student is assigned there, okay? So what would an example of that be? Well, let's go back to the very first example outcome that we talked about, where student 1 gets their first choice, school 2, 2 gets their first choice, school 1, and student 3 gets their third choice. We said that's an efficient outcome because there's no way to make students better off without hurting other students. But is this an outcome that has no justified complaints? Well, if 2 students are getting their first choice, they're not going to complain because they're getting their first choice. So the only student who could complain here is student 3. Now, would we say that a complaint from student 3 is justified? Well, student 3 would complain and say, I got my third choice. I'd rather have my first choice, S1, or I'd rather have my second choice, S2. Am I more deserving than someone else at one of those schools? Okay. So let's go through the 2 possible cases here. Student 3 says, I'd rather get S1, my first choice, than the school you've assigned me to, my third choice. Who's assigned to school S1? Okay. Well, in our example, imagine that student 2 is assigned to school S1. Okay. So who's more deserving of school S1? This is now where we go to the school priorities. Okay. We look at the school priorities and say, well, the most deserving, according to the priorities at school S1, is student 1, followed by student 3, and the least deserving is student 2. So student 3 goes back and says, hey, that's not fair. I have a higher claim to school 1 than student 2, yet student 2 got the school. Okay, so I'm going to call up the district. In fact, I'm going to sue the district and say, your policy was to give me higher priority than student 2 at school 1, yet student 2 got school 1 and I did not. Okay, you gave me my last choice. That's against the policy. The priorities of the schools place me higher than student 2, so my complaint is going to be justified, and we could run into some potential trouble. Okay, so here's a situation where we would have an outcome that's efficient, but one that allows for justified complaints. Okay. So I hope you see here, there are these two different notions. One is just focused on the student side. Let's try to give as many students as possible a high rank choice. And the other that's looking at a little bit more at the school side and saying, are we actually implementing the policies embodied in the school priorities, okay? And here is where we run into our trade-off, what I alluded to earlier. If we focus on systems where honesty is the best policy, we have property 2, the efficiency property, assign as many as possible a high choice. And we have property 3, which is the no justified complaints property, which I've paraphrased as let's implement the district's admissions priorities. We can't have it all. Okay, so there is no system that will satisfy all 3 of these properties together. Honesty is the best policy, assign as many as possible a high choice, and implementing the district's admissions policies, okay? And that's a mathematical fact. I don't have time to explain that to you, but if you want some more details, I'd be happy to tell you, aside from this webinar, why that's true. So what's important for us is there's this trade-off. We can either have property 2 or we can have property 3, okay? So when you think about what a school committee or an admission system wants to do, we have to weigh these two competing goals, okay? And so this is a great place for me to get feedback from those of you who are on the line. I want to ask you the following poll question, okay? What do you think is more important? First, efficiency, again, assign as many as possible a high choice. The no justified complaints idea, there's no student afterwards who can say, I should have got something I'd rather, I ranked higher, and the system says my priority is higher at that school than someone who did get it, okay? Number 3, it depends. And then number 4, neither. So let's launch our poll here. And I'm very curious to hear your feedback on which properties you find most compelling.
I'm having just one technical challenge launching the poll here. It's telling me it can't start the poll because another poll is in progress, but I don't believe that's true. So we may have a technical hurdle here. Yeah, nothing sharing. Huh. Well, I think we have a technical glitch here. It's not, won't let me launch the poll. So actually, if you'd like to, maybe this is an opportunity for some more interaction, maybe comment in the chat and let us know which you think is more important, the efficiency or no justified complaints or something else.
Great. So Suchitra Saxena says, having worked for the New York City Department of Education, I will vote for number 2. And that's terrific. And I'll explain a little bit more. New York actually implements a system where property number 2 is satisfied. There are other cities, however, that implement a system where property 1 is satisfied. Anyone else want to tell us in the chat what they think? Again, there's no right answer here. That's a bit why this is an interesting and challenging problem. These are situations where there's no right answer. Okay, great. Well, why don't I keep pressing ahead? Yeah, so there's another comment here about no justified complaints. Someone says, I like the idea of efficiency, but the cost is too high for students that don't get their first choice. You know, let me tell you a little bit more about how we can implement these different kinds of outcomes. And that leads me to 2 other processes that I want to describe, and please keep chatting if you'd like. We've already talked about the immediate acceptance idea, and so I want to talk about 2 other algorithms that are really central in the school assignment area. And so the first one is what I'm calling efficient exchange via top trading cycles. Okay, so that's a mouthful, but the key word is the first word, efficient exchange. So this is a system that is going to lead to an outcome that's efficient. And what it's doing, before I read this to you, is trying to find swaps between students such that students are getting higher rank choices by trading with each other. Okay, so in TTC, we have every available school pointing to the highest priority individual among all individuals. And every individual points to their most preferred school, okay? So this is pointing, that's a way of saying, I want to trade with the person who's got the highest priority at the school that I want the most. And so what we look for is a cycle, which is a collection of students who want to trade with each other, okay? Whenever we find a cycle, we assign each individual the school that they're pointing to in the cycle, and they're finalized, they're done, okay? And we would decrease the capacity of the school. If a school runs out of seats after trading, we'll remove it along with the individuals in the cycle from the problem. And then we iteratively look for trades here, okay? So you might say, this sounds really complicated. I want to explain this is actually not as complicated as it sounds by showing you that example again, where we're going to look for trades and we're going to look for cycles, okay? So in our example, it's the same setup as before. So student 1 likes school S2. So that's why I have I1 pointing to S2. And the other 2 students both like school S1. Okay. So that's why they're pointing to it. Okay. So what do we do next? What we do next is have the schools point to the students who have the highest priority. So school 1 points to student 1. Because student 1 has the highest priority at school 1. School 2 points to student 2, and school 3 also points to student 3. So where's our trade here with all of these arrows? Well, if you look hard enough, you'll see that the trade is right here. Student 1 wants school 2, who's pointing to student 2. Student 2 wants school 1. And school 1 is pointing to student 1, completing the cycle. So we can allow students 1 and 2 to trade with each other, okay? And when we implement that trade, both the students end up getting their first choice, okay? So we remove them, that's why they're grayed from the problem. And all we have left now is student 3. Student 3 will point to their most preferred choice, but it's going to be their most preferred choice among what remains. And at this point in the process, only school 3 remains. So student 3 points to school 3, school 3 points back at student 3. We have a cycle. This is a cycle with just one person, okay? And student 3 ends up getting their third choice. So at the outcome, at the end of this, the outcome is the outcome where 2 students get their first choice and 1 student gets their third choice, okay? So this is an example of efficient exchange. You'll see that there is no way to make a student better off without hurting a student. The first 2 students get their first choice, so there's no way to take them away without making them worse off. But this is the same exact outcome that I just went through a second ago, which allows a justified complaint by student 3. Student 3 could go to the school board and say, I should have gotten school 1, and I have a higher priority than student 2 at school 1. It's not fair that the students 1 and 2 traded with each other to get their top choices when I had a higher claim, okay? Now, let me turn to a second case study, a place where the top trading cycles system was actually implemented, and that's in New Orleans, okay? So New Orleans is an interesting setting in the 2000s, especially because they had a school district that was called the Recovery School District, the RSD. Even though it's called the Recovery School District, it was actually formed before Hurricane Katrina struck the city in 2005. The Recovery School District was part of a plan for state control of schools in New Orleans. And New Orleans attracts a fair amount of attention in education reform debates because in 2012, It was the first district in the nation to integrate assignment between traditional public and charter schools. So New Orleans and Denver were the two cities that did that. And a couple years later, the district became 100% charter, okay? Many officials who worked in New Orleans had worked in New York City earlier. And so as part of the reforms in this era, they decided to move to a single best offer assignment system that's known as One App, okay? And that system exists to this day. And in fact, the team at Avella is working with folks in New Orleans to try to make a better school finder product, the Avella Explore product for them. And in New Orleans, officials decided that all recovery school district schools would use a simple prioritization. There would be a sibling priority and a walk zone priority, and a random number would break ties within applicants. Okay, so here's a description from the newspaper at the Times of this algorithm. Okay, so on the left, we have a scenario where school A points to student one, and student one's first choice is school A, so there's a swap just involving one student. Scenario B is one where we have a trade between three students. Okay, one is pointing to B, B points to two, two points to C, C points to three, and 3 points finally back to school A. So you can see that at a high level, this algorithm is basically an organized procedure to find ways to implement mutually beneficial swaps, okay? And this procedure is one where honesty is the best policy, okay? There's no reason for you to strategically misreport what schools you want. You don't have to consider the popularity of schools, because when it's your turn to trade, you will be trading with the most preferred school that still has capacity left over, okay? And we also produce an efficient outcome. Turning now to the last algorithm I want to introduce today. This is called Deferred Acceptance. It's named after Gale and Shapley. So Lloyd Shapley was awarded the Nobel Prize in 2012 in part for inventing this idea. And the key expression I want you to pay attention to here is the word deferred. Okay, so deferred is different than immediate acceptance, because in deferred acceptance, placements are not finalized until the absolute end of the process. Okay, whereas in immediate acceptance, if you are accepted at your first choice in the first round, you are done, you're immediately accepted. So how does DA work? In step one, each student proposes to her first choice. Each school tentatively assigns its seats to its proposers one at a time, following their priority order, and any remaining proposers are rejected. Okay, so the key word here is tentatively assigns. Okay, so in the general round, each student who was rejected in the previous step will propose to her next choice, and each school considers the students it has been holding from the previous round together with these new proposers, and accepts them tentatively one at a time according to their priority order. Any remaining proposers are rejected. Okay, so the whole idea here is quite different than looking for swaps between students. This is an application and rejection process where it's possible that someone who's listed as school 10th applies and causes the student who's listed that same school first to be rejected. How could that happen? Well, the student who's listed at school 10th has been rejected from all of their first 9 choices. That's why they go on to apply to their 10th choice. And they must have had higher priority than a student who had listed it first to be able to displace them. So you can imagine that this system is going to do a better job at implementing the district's priorities or eliminating justified complaints. So let me show you how this works out in our example. Again, this is the same exact example. And here I want us to reinterpret the pointing to be an application. Okay, so in the first round of deferred acceptance, student 1 is going to apply to school 2, okay, S2, and students 2 and 3 will both apply to school S1, okay? So what happens next? School S1 has 2 proposers, but just 1 seat. So school S1 considers their priority and sees that student 3 has higher priority than student 2. So we end up with student 2 being rejected, and tentative assignments, that's why these are dashed lines, placing student 1 tentatively at school 2 and student 3 tentatively at school 1. So student 2 has been rejected will propose or apply to their second choice, S2. Now, S2 has to decide who is going to be tentatively accepted. Is it going to be student 1 or is it going to be student 2? So according to the priority, it's got to be student 2 because student 2's got the highest priority. So now student 1 is rejected. Student 1 will go on to apply to their next highest choice, which is school S1. S1 considers their priorities. The priority places at S1 places student 1 first. So now student 3 is rejected. So in this example, all 3 of our students have been rejected. And student 3 will then go on to apply to school S2, where she's rejected, and then eventually to S3, their third choice, okay? At this stage, all of the tentative assignments are finalized because there's no new rejections, okay? And we end up with the following outcome. Student 1 and 2 are actually assigned their second choice, and student 3 is assigned their third choice in this. So unlike the previous examples we've been talking about, no one is assigned their first choice here, okay? Now, the top trading cycle outcome that we just talked about had students 1 and 2 actually trading with each other. If you look at the outcome here, student 1 wants school 2 as their first choice, but they got S1, their second choice. And likewise for student 2 wants school S1 as their first choice, but they got their second choice. So why not trade? Okay, why not allow the students to swap with each other? Well, the reason we don't allow for that is because of student number 3. Student number 3 says, you know what? I know you guys are both getting your second choice. You guys both could trade with each other and get your first choice. I wouldn't be affected. I'm still getting my third choice. But I'm going to block you guys from doing that because that's not implementing the district's policy. The district's policy says I get higher priority than student 2 at school 1. So there's no way for us to allow that kind of trade without violating the district's policy. So here, what I want you to see is that there is this real tension between trying to give as many students what they want, okay, and having a situation where no student can complain, okay? And as we talked about earlier, in New York City, deferred acceptance is used both at middle school and high school. And this, of course, is a famous algorithm where we're iteratively going down each school's rank order list and only finalizing placements, deferring all tentative assignments until the very end when there's no new rejections. And in this system, honesty is the best policy. And we never have a justified complaint. But as we've just seen, the outcome will not be efficient necessarily, okay? So just again, to summarize, within the class of algorithms where honesty is the best policy, we face this trade-off. Do we maximize the choices of students like top trading cycles does? 2 students get their first choice, 1 got their third choice. Or do we eliminate justified complaints, even though we could have made 2 students better off without hurting anyone else? Okay, like deferred acceptance. So let me ask you guys, let's see if we can get the poll up and running here. Which algorithm do you think is better? Deferred acceptance, top trading cycles, immediate acceptance, or none of the above, okay? And finally, it depends, okay? And we have cities that have used all 3, including cities, actually, I should say all 4. There's some cities that have come up with even other types of procedures. So if you could just take a quick moment to fill that out.
Grog, we need to get some Jeopardy music for the next time.
Yeah. Well, it's, just, I think a couple more people need to fill out. There we go. Terrific. So sharing the results. Oops. Do you guys see the results here? I can just summarize it for you.
Yeah, now it's saying failed to share poll results.
About half of the 50% of folks said deferred acceptance, about 30% said top trading cycles, and 20% said it depends. Okay, that's exactly what we expected. Now, let me tell you about what we know from the field, and then I'll tell you about a city that changed from one algorithm to the other. So you might be wondering, what exactly is the cost of eliminating justified complaints in terms of student choices? Is there really a trade-off? It's nice that I can construct these examples with 3 students and 3 schools, but are these realistic examples? Well, in Boston and New York City, the evidence that we have so far is that An efficient system like the top trading cycle system slightly increases the number who obtain their top choice, okay? And how do we know that? Well, this is a side benefit of having a system where honesty is the best policy. We can simply take the data from these systems and run a different algorithm. And because it's an algorithm where people are honest, it's a good assumption that people would not rank schools very differently under an honest algorithm. Okay, so there is a slight gain in the number who obtain their top choice under an efficient system in Boston and New York. Boston and New Orleans. In New York, on the other hand, there is a big difference between deferred acceptance and top trading cycles. With an efficient system in New York top trading cycles, we would have a much larger effect on the number who obtain their top choice. So it's on the order of 15 to 20% more kids would get their top choice. So why is there a difference? Why is New York City a place where there's a bigger wedge between these two procedures relative to Boston and New Orleans? And our best guess right now is that difference is likely driven by the fact that New York City has many different types of school priorities than Boston and New Orleans, where the priorities are simply based on sibling and walk zone status, especially in the early years in New Orleans. In New York City, on the other hand, there is priorities based on schools that rank students based on auditions and interviews. Some schools historically have had a priority based on attending an open house, and so on and so forth, okay? Now, so, if we go back to the question that we asked in the poll, which algorithm do you think is better? I think what we're learning is it depends. It depends on the priority system in the city and when we expect these differences to be large versus be small. Now, the last thing I have on this slide is some details about what happened in New Orleans. So actually, New Orleans switched from top trading cycles to deferred acceptance in 2012 for a couple of reasons. One of the reasons involved the addition of new schools in the system. So initially, the Recovery School District simply had schools that had priorities of sibling and walk zone, okay? And in 2012, the city welcomed schools in the Louisiana Scholarship Program. So that's a statewide program which sends students to private schools. It pays for their tuition at private schools. And placement took place in the same exact algorithm. So there was a state law that was passed that was interpreted by the state's council as not allowing for situations of justified complaints because the scholarship schools actually had a much more elaborate prioritization that depended on eligibility requirements of students, their income eligibility, and the quality of the schools that they were currently attending, okay? The other thing that happened in New Orleans is the Orleans Parish School Board, which was another parallel school district that existed at the time, operated a handful of schools that had more complicated priority structures, including priority structures where students were interviewed and they had to audition, say, at the art schools. And that brings us a little bit closer to the New York City situation. When you have schools that rank applicants, you might think that justified complaints are a bigger problem because it's not just the student who's complaining, but if a school is ranking the student, the school will also complain and say, I wanted this kid. Why did you give me someone who's lower ranking? So that was a big part of the decision in New Orleans. A second part of the reason New Orleans stopped using top trading cycles is that deferred acceptance seemed easier to explain to participants. Now, it's important to remember both of these systems are strategy-proof systems, so honesty is the best policy. The only advice you have to give is rank schools truthfully. That's a mathematical theorem. It's a mathematical result. But when people wanted to know about the nuts and bolts of why they got assigned, where they got assigned, officials in the district thought that deferred acceptance was an easier thing to explain. Okay, so since 2012, New Orleans has been using a version of the deferred acceptance system. So wrapping up here, a couple of points that I'd like you to take away. First, we've really taken a deep dive into one part of the school choice process, which is the algorithm. We haven't talked about the inputs of the algorithm and what happens after offers are made, but we believe the algorithm is the foundation of a well-functioning school choice process. There's three properties that we talked about that I want like you to remember. First is honesty is the best policy. There's still many districts across the United States where that's not true, and that creates severe inequity. Then we have this trade-off between giving as many students as possible a top choice and having no justified complaints. We believe an honest algorithm has many virtues. It's easy to give people advice. It's levels the playing field between participants who may be in the know and those who are not. And it's possible to simulate scenarios. And how we feel about other criteria depends on our policy aims in the local context. Okay, so today, it's just a high-level overview, and there are many important details. We hope to get to those in future webinars, things especially related to diversity policies and walk zone reserves and ways that we keep families together. But let me stop here. Thanks so much for your attention. And I'll hand it back over to Greg to wrap us up.